Hello, hello. It is time for lecture 16. 16, or depending on how your screen works, 16. Yes, lecture 16, whereby we go to the next level as far as how and why does the sun shine. Remember, our course on contemporary theories of the solar system is trying to get us to the scientific theory that explains that key thing. Why does the sun shine, right? And we've gone through some calculations. It's all based on these cool things about figuring out certain aspects of how the universe works. And it all is driving toward this amazing result of why and how the sun shines, right? We've gone through up to this point, remember, where we tried to use Lord Kelvin, his hypothesis, which turned out to have some traction, but didn't quite work out because when you use the correct number of the gravitational constant of the universe and the correct number for the mass of the sun and the correct number of the diameter of the sun, the total amount of gravitational potential energy that could come out of the sun by its collapse is this many joules, about 4 times 10 to the 41 joules, which meant that overall, based on the current luminosity of the sun, right, 4 times 10 to the 26 watts, 4 times 10 to 26 joules per second, it would last about 30 million years, which is just too short because we now know, starting in the 1900s or so, in the late 1900s, certainly mid 1900s for sure, but like even by the early 1900s, it was clear that the Earth was older than 30 million years. And in fact, at least billions of years old. So what was next? We need to find a different energy source. And that energy source comes from the atom. Now, this is the cool part, right? We're going to get almost to this point about how the sun shines and why it does. And getting to that point is a really neat part in the history of astrophysics, astronomy, science in general. And here's where it comes from. The idea that atoms even exist is actually a relatively new idea in the world of science. As late as the mid 1930s, and I might have mentioned this in passing in a previous lecture, the idea that an atom even existed wasn't in chemistry textbooks in general. Most people thought that there was likely to be an atom, and there was experimental evidence to show that atoms existed, but you could do chemistry, you can do biology, you can do even most of physics without having to think about atoms. And as you know, atoms have the nucleus in the middle and then the orbits of electrons around it, right? And the nucleus contains protons and neutrons. That's the overall structure of the atom. The idea of an atom was still a hypothesis that had been proposed and predictions had been made, but it had not been falsified yet. A lot of people were trying to falsify the idea of the existence of the atom. Today, after all those attempts, it's quite clear that not only was it not falsified, but it is confirmed that matter is made up of atoms here on Earth, right? But the atomic theory was still in its infancy on a scientific level as they were trying to do that kind of thing in the 1900s, the early 1900s. And so there were a lot of people trying to figure out, do atoms exist? And what happens with them? Are they it? Can you make things bigger? Can you make things smaller than atoms? Right? Those are the questions that eventually, over time, led to our understanding of how the sun shines. So let's get to that point. The year is approximately 1901. Okay. Now there's this 22-year-old smart guy. He's born in Germany, and his family moved to Switzerland because his father was like a tech entrepreneur at that time, trying to work on the new technologies of like radio and wireless communications and stuff like that. And he was a smart guy, this guy, but he wasn't like the best student. He was a very good student, but he wasn't considered like the best student. And that was because he would get distracted a lot. He'd do a lot of different things, and he came up with these ideas that people said, you know, that's a little creative, but that's also not quite straightforward. It seems kind of unusual. And in 1901, he was a graduate student in Switzerland at a university, the Swiss Technical Institute, kind of it's ETH in English, ETH in the Swiss language, German, French kind of thing, ETH. And it was like the MIT or the Caltech of Switzerland. Still is, actually. But this guy, he wanted to do some interesting work in about 1901 to do a PhD thesis. And he was turned down. He said, no, this is kind of cool, but your idea, I'm not a big fan of it. So he was turned down to do a PhD thesis about 1901, 1902, and he was kind of discouraged. But he came back. He changed his mind. After about a year or so, he said, you know what? I do want to finish my PhD thesis. I want to get a dissertation done. I want to be a Dr. Albert Einstein. And so he, in fact, in 1905, to support himself and his family, instead of having a fellowship from ETH, he instead was working as a patent clerk in Switzerland. And so he was supporting himself as a patent clerk and also doing this other work in his science and so forth. And in the year 1905, his work all came together. It was really remarkable. Many people still call it the year of miracles because Albert Einstein published so much cool stuff. Okay. And that is where we start now, this next phase of trying to understand why the sun shines. Okay, let's go to it. I'm going to share my screen. I'm going to show you a historian of science analyzing or talking about Albert Einstein's research and what he did as he was turning into what many of us consider today the synonym to brilliance and intellect, right? You can also see some of this information in section 16.1 of the textbook, all right, the sources of sunshine, and 16.2, thermal and gravitational energy. Now, the previous lecture is the 16.1 section. I want you to read this, right? And we talked about Watt, conservation of energy. Oh, there's Lord Kelvin on the left and that Helmholtz guy on the right, Hermann von Helmholtz, and about the gravitational potential energy and the thermal energy and so forth. That's 16.1. And here we go, 16.2, which we can read later. And I encourage you to do so because that will give you a lot of information about what we're doing here, about mass, energy, and the theory of relativity. Okay, I'm going to switch to this tab. This historian, Norbert Straumann, who is a physicist and a historian, wrote this paper describing Albert Einstein's PhD thesis. Remember, his first PhD thesis was turned down, and he almost gave up on graduate school. He's like, I'm really tired of this game. He didn't like it. But he realized that he really loved science, and even though it was like irritating to deal with like the bureaucracy of the school and so forth, he stuck with it. He came back to it, and while he was working as that patent clerk, in 1905, his science came together. And so he wrote 5 papers. One of his papers, the second one that was published, is actually his PhD thesis, right? Where he actually figured out something very useful about the fact that atoms actually exist. See, typos, a new determination of molecular dimensions. And he had done some calculations. He didn't get it right. He figured out that he had made a calculational error and went back and fixed it. And then he figured out like the Avogadro number that had been proposed, right, but not been confirmed yet. And people were trying to falsify it or figure out whether it's true or not. And he basically was able to confirm through his calculations that the Avogadro number was basically correct, which is so cool. And then after that, he got his PhD, finished his thesis. And from that idea of Avogadro's number and the sizes of molecules and atoms, he then submitted a paper on Brownian motion, which is often described in physics and in chemistry also as conclusive proof that atoms and molecules existed. All right. From there, atoms and molecules and the fact that there are these little things moving around, which is great, right? Then he said something really cool in 1905. Atoms and molecules not only exist, but by chance, they actually can turn into energy. In other words, matter and energy are interchangeable as long as you have a conversion factor. Whoa, that's an amazing thing. We'll talk not a whole lot about the derivation of that relationship, which is so famous and so well known. But just know that that was like 1905 was something that he came up with. He realized as he was working on trying to figure out how the relationship between light, which is a form of energy, and atoms, right, which are a form of matter, how they were interacting with one another, he came up with this mathematical derivation and said, hey, everybody, guess what? If I make this hypothesis about how atoms and molecules work, then what happens, one prediction of that hypothesis is that energy and matter can be exchanged, that they can go from one to the next. Kind of like if you're translating, if you're changing British pounds to US dollars or euros to Japanese yen, that kind of thing. Okay, so I'm going to write down the equation, which you've all heard of before, probably the most famous equation in all of science, certainly in physics, right? And this is a very, very commonly quoted and cited equation. Many science books are written in such a way that that's the only equation that shows up in it, right? And it's so big and so cool. I'm just going to write it huge, and you all know what it is, don't you? E equals mc squared. The energy of a bit of matter is the matter times the speed of light squared. Okay? Now, I might have mentioned this in other lectures before, like just in passing, but let's break down this equation very, very carefully. What he basically said was that if you have a blob of mass, okay, let's say you're measuring that mass in kilograms or whatever you wish, grams, if you multiply that m, that mass, by the speed of light squared using the same elements, the same units, then that's how much energy you'll wind up getting if you convert that matter all the way into energy. So C is the speed of light, right? C is 3 times 10 to the 8 meters per second. And so C squared is 3 times 10 to the 8 meters squared per second squared. Now, what does that mean? Oh, wow. Well, remember that if I measure kilograms, right? If I measure mass in kilograms, let's say this is typically in kilograms. Then if I take a number and multiply it kilograms meters squared per second squared, then energy is in the units of kilograms meters squared per second squared. And guess what? That energy unit is a joule, okay? So that big letter J, or the lowercase word joule, right, named after James Joule, that unit of energy that you get when you take 1/5 of a water bottle of water and move it up a meter and then drop it in your hand like that, right? That's 1 joule worth of energy that just hit my hand, all right? That joule is a kilogram meter squared per second squared. Okay, meters, a kilogram meters squared per second squared, or joules. So this is a really interesting equation, all right? Because think about this. Let's do an example, like how much energy do you get from converting a certain amount of stuff? Remember earlier, we were talking about the atomic bombs at Hiroshima, right? Remember that the sun produces trillions of atomic bombs worth of energy every second, right? And it was just an amazing amount of energy. But an atomic bomb is a lot of energy already. Like remember, wiped out a city in a fraction of a second, right? 5 times 10 to the 13 joules. Let's do the E equals mc squared on an equation and see how much that actually is. All right, let's try it. So as an example, an atomic bomb, tremendous amount of energy, right? 5 times 10 to the 13 joules. How much matter needs to be converted into energy to produce the energy in an atomic bomb? Okay, how much matter? I mean, atomic bomb's like a big device, right? The planes in World War II back then could only carry one at a time. It was a huge piece of machinery, and it was designed to convert matter into energy to produce an explosion. So if we use E equals mc squared, right? So 5 times 10 to the 13 joules, and let's say that equals mc squared. So equals mc squared. I'll put mc squared. That's the amount of energy, right? How much is m? Remember that c squared is 3 times 10 to the 8 meters per second quantity squared right here. All right, so let's plug it into the equation. So that equals m times, I'll use a different pen here so we can make it clear. 3 times 10 to the 8 meters per second squared, like that, right? Remember that this m is the unit meters, that m is the mass that needs to be converted to create this many joules. So let's multiply this out, right? And that turns out to be 2 equals, let's me use a completely different color pen so that I can just make sure that we don't use any of this stuff. Thank you. That equals m times 9 times 10 to the 16 meters squared per second squared, like that. Okay, remember that a joule is a kilogram meter squared per second squared. So I'm going to divide both sides by 9 times 10 to the 16 meters squared per second squared and see what I get. Okay, so 5 times 10 to the 13 joules divided by 9 times 10 to the 16 meters squared per second squared equals m. Right, so I've divided both sides of this equation, that and that, by 9 times 10 to the 16 meters squared per second squared. Just have m on this side, just have that equation over there. What is that number? It's not that big, is it? Let's see. I think that m equals 5.56. Just going to 3 significant digits from now, times 10 to the minus 3 kilograms equals m. Excuse me, 10 to the minus 4 kilograms, like that, right? Because this is 0.555 repeating, of course, times 10 to the minus 3, which means it's 5.555 repeating, or in this case, 5.56 times 10 to the minus 4 kilograms is m. That means it's half of a gram of matter, okay? This is 5/10,000ths of a kilogram, so it's about half a gram. Now, what object is typically about half a gram? Paperclip is typically 1 gram. So a paperclip, if you broke this paperclip in half and converted all of that matter into energy, you get an atomic bomb. Pretty amazing, right? All you need to do is have a tiny, tiny little bit of matter, and you get a huge amount of energy. That's what E equals mc squared is all about, right? So matter, this stuff that we're made out of, this crude material, right, actually is a very, very concentrated form of energy. It's been changed and adjusted in such a way that it exists as atoms, as particles. But if you were able to liberate all that energy that was packed into those atoms and molecules and matter in general, then you get a huge amount coming out. See how that works? That's the power of E equals mc squared, which is really cool. But back when Einstein figured this out, right, in the early 1900s, the question was still, how do you get it out? But the question, first of all, was, can you get it out? Is there something, can you actually confirm the existence of something like this? Can you actually show that E equals mc squared? The answer is yes, because we made atomic bombs, right? For whatever, good or bad in the history of humanity, we have experiments, we have proof, we have evidence that confirms that E equals mc squared. But that conversion is not easy, right? Remember, the technology required to turn that matter into energy is very complicated. Remember, the entire atomic bomb, remember, it was so big, it was thousands of pounds, right? That's a machine, basically, to convert energy. But in the end, all it did was converted half a paper clip's worth of matter into energy. All the rest of it, all the design, all the extra stuff was all designed to convert half a paper clip's worth of matter into energy. That's amazing, right? I think it's amazing. So that technology, that physics, right? How you make those conversions is very, very important. You can't just do it because you feel like it, right? There is all kinds of scientific and engineering type stuff that are involved to make it work. So there are two basic kinds of ways that you can get matter out of energy. It turns out that if you do the arithmetic and the mathematics and things like that just right, you can figure out whether or not the sun can be powered by this amazing energy, right? Because realize the sun, right, has a mass, remember the solar mass is 2 times 10 to the 30 kilograms, right? More than 300,000 times the mass of the entire Earth. So that's actually pretty good. If you figure out how much energy that comes out, right? You take this and multiply this by c squared, you get 10, 20, well, let's see, just off the top of my head, I'll make you do this or some version of this on the study guides, because you should be practicing this kind of conversion of matter to energy. And in fact, you may already have done some of this. If you haven't, remember, if you haven't started the study guide yet, do it now, right? Fill it in. And then do the rest of the study guide later, because that's an important part of the course and everything. But if you take that 9 times 10 to the 16 meters squared per second squared, right, the c squared multiplied by this, then you get something like 2 times 10 to the 47 joules. And remember that 10 to the 41 joules would last about 30 million years, right? 10 to the 44 joules, based on the number, if we had not made the correction, right, and done it wrong, it would have been like 30 billion years. But we're talking about 10 to the 47 joules, which would mean that there's way enough matter in the sun in order to power the sun at its current rate for easily billions of years, many billions of years. So if there were a way that this E equals mc squared equation could be applied in the sun, then we would be able to confirm that the sun is powered by this E equals mc squared reaction. Okay? The two basic ways that we humans know of to turn matter into energy, right? There are two basic ways. I'm going to write one in the upper left-hand corner here and the other in the upper right-hand corner of the E equals mc squared equation, so you know what I'm thinking about, okay? The first way that we know about is called nuclear fission, F-I-S-S-I-O-N. You may know this word already, this nuclear fission word, from maybe a biological perspective. Actually, when cells divide, sometimes that's referred to as fission, because fission means dividing things up, right? A fissure is like a crack. It's a separation between two pieces of something. So the idea is you take some matter, take an atom, for example, maybe uranium, maybe plutonium, something like that. And then you find a way to make that thing break up. Now, when you have an atom, remember, E equals mc squared, right? This is a lot of energy that's been sort of turned into a blob of matter. And if you find a way to split that chunk, split the atom, right, into two smaller atoms, subatomic particles and things like that, then some of that energy will be released, because when you split these big heavy atoms, right, plutonium or uranium or something like that, the result is you wind up with a little tiny bit of that matter that used to be part of the nucleus disappearing and turning into energy. And it converts. You go from matter to energy. So you still have a lot of matter left, right? In fact, if you have like 10,000 grams of plutonium or something like that, right? You might wind up with a half a gram of energy, because the rest of that matter, 9,999.5 grams, is just become different kinds of matter, right? And then only half a gram, half this paperclip, was actually converted from matter into energy. So, that's still ridiculously powerful, right? I mean, it's amazing how much energy came from those atomic bombs. And in fact, when we talk about nuclear energy today, right, there is still that idea. You take uranium or you take plutonium, fuel rods or pellets or whatever, and you just convert little tiny bits slowly but surely, and you get electric power. A lot of us living in the greater New York metropolitan area get up to 100% of our electricity from nuclear power plants. It's through a controlled, not an explosive, but a controlled fission reaction going and using that E equals mc squared method. Yeah. So that's one way to do it. That's fission, right? Now, what you need for fission is a lot of heavy elements that have the ability to split up into smaller atoms, right? We don't know how much stars have. Stars tend to, like the sun, right, not have that many heavy elements. And that was one of the things that tried to figure out at that time. There is an astronomer around the same time that nuclear fission was being discussed. All right, there was an astronomer, and her name was Cecilia Payne. Let me write her name down because she is very cool also. Let's see here. Use this blue colored pen. Cecilia Payne was a very interesting character. She showed brilliance as a college student, but she lived in a time in the early 1900s, right, where women were not allowed, for no good reason really, just tradition, to get advanced degrees in anything, especially science. But she was British, and she went to Cambridge University, and she did really well in science. So here she is, like in her early 20s, and she wants to go on and do a PhD. She wants to do cool physics and stuff like that, right? But Cambridge University wouldn't let her. But what happened was the foremost astrophysicist of his time, back in that period of time, the early 1900s, was a British guy named Arthur Stanley Eddington. And Eddington was in Cambridge, and he said, you know what? I'm so sorry. We're not going to be able to allow you to get a PhD or do research here in Britain, but maybe in America you can. And so Cecilia Payne, with this introduction letter from Arthur Stanley Eddington, went across the pond from the UK, Cambridge, England, to Cambridge, Massachusetts, and Harvard College Observatory. And what happened was that the director of the observatory at that time was a guy named Harlow Shapley. All right. Now, if you take Astronomy 102 at some point in the future, or if you've already taken it, then the name Harlow Shapley is someone that you recognized before, right? Shapley is a great astronomer and a great humanitarian, just a good guy all around. And we were very fortunate that he was part of the history of astronomy and astrophysics. And what happened was that Harlow Shapley said, yes, Cecilia Payne is excellent and should get a PhD. But Harvard physics doesn't allow women to get PhD either. Therefore, we are going to create a PhD in astronomy and astrophysics, and we won't care whether or not men or women get it. So Cecilia Payne became the first woman to get a PhD in astronomy or astrophysics at Harvard. And she basically turned the world of astronomy toward the future. She did a great job in all the science that she did in her life. And she's just a tremendous scientist that everyone in the field of astronomy remembers fondly and really honors. So this person, Cecilia Payne, she eventually married a gentleman named Sergei Gaposchkin. So in later years, her name was Cecilia Payne Gaposchkin. But you'll remember this name, Cecilia Payne. She, in her dissertation work, in her PhD work, showed that the sun is made primarily of hydrogen. Hydrogen, remember, if you know your periodic table, right, it's got one proton and one electron going around it. Sometimes it might have another neutron in it. Sometimes it might have two neutrons in it. But basically, it's one proton and one electron. It's very simple. You can't break it down. So nuclear fission, if the sun is made up of hydrogen primarily, you can't turn that into heavier, lighter elements because it's the lightest one. All right. So there just wasn't enough heavy elements in the sun, people understood, in order to use fission as a way to get energy by the equation E equals mc squared. So fission, it's cool. Here on Earth, we use it, as human beings, but in the sun, not so much. So what I'm going to put over here is what can happen if you use hydrogen to create energy by E equals mc squared. And that is the exact opposite of fission, which is nuclear fusion, right? Now, what is nuclear fusion? Also possibly another word that you've heard of before. We humans, by the way, also know how to make bombs using fusion, all right? It is what it is. We human beings have figured out how to make bombs pretty well. And one of the ways that we can make an atomic bomb is not just through fission, but through fusion, which is you take hydrogen, right, and other light elements and make them into heavier elements. When you put light elements together, turns out that some of the matter, some of the mass of the light elemental atoms disappears too. It gets converted into energy. Isn't that interesting? So what you have to do is to get a circumstance where you can get fusion to happen, and then maybe by E equals mc squared, you can cause the sun to shine. Okay, fusion, not fission. Fission, don't have the raw materials. Fusion, though, you do have the raw materials. But fusion is really hard, right? Like I said, we today know how to make bombs out of either fission or fusion. But the sun is not a bomb, right? The sun is a system that goes on and on and on and on and produces 4 times 10 to the 26 watts of luminosity and has been doing so for billions of years. You need special circumstances in order to make that sustain for a long, long, long time. So how do you do it? Well, that's a great question. And it eventually fell to a scientist. His name was Hans Bethe. Okay, we pronounce it Bethe. He's German, Hansbethe, Hans Bethe. All right, and I'm going to tell a little bit of the story of Hans Bethe, and then we'll get a sense about how nuclear fusion can work out. Basically, Hans Bethe, very talented German physicist. He was really, really good. And in the 1910s, he was a student, 1920s. He was a really great researcher. And then in the 1930s, when the Nazis took power in Germany, his mother is Jewish. Although they didn't practice Judaism in their family, he knew that he had to get out. And it turned out that he was able to get to America in the early 1930s. Cornell University basically said, hey, why don't you come and be a professor here? And so he spent most of his adult life, he lived well into his 90s, at Cornell University in Ithaca, New York, where he did a lot of cool physics. Right, in the same way that Cecilia Payne came to America, but not to Cornell, went to Harvard, Hans Bethe went to Cornell and did a lot of cool physics, this time about nuclear physics. Right, he did a lot of research about nuclear physics, and he figured out that although there was no good laboratory way to cause nuclear fusion to occur for sustained periods of time on Earth, there was a possibility, there was a way that you could go ahead and cause fusion to occur inside the hearts of stars like the sun. The key had to do with the nature of atomic material itself, because this is something that you'll come up with later, but I'll mention it right now. Turns out that if you are trying to look at atoms and molecules, they're very, very small, remember. They're itty bitty. And as a result, they follow different rules of motion than the planets and the moons. You know, Newton's laws of motion don't work when you're talking about systems that are a billionth of an inch across or so, right? A millionth of an inch. At that level, Newton's laws, F equal ma, still kind of work. But the ability to try to figure out exactly how they work, you can't measure things at that level. It turns out that the way that things move and the way that things get energy at those levels follow a whole different set of physical laws. And that was what Hans Bethe was a specialist in. That area of thought, okay, it's called quantum mechanics. And this was the cool stuff that led to our understanding of nuclear fusion. And I'm going to write down the word quantum mechanics at this point. And when you are doing your study guide and watching stuff, you're going to learn about quantum mechanics. And quantum mechanics is really, really neat. But it is quantum mechanics that Hans Bethe was a specialist in, right? In the way that Cecilia Payne was a specialist about the hearts of stars and what they're made of. Hans Bethe figured out that under the right circumstances, the rules of quantum mechanics allowed nuclear fusion to happen in a sustained way inside a star like the sun. That's amazing stuff. And it has to do with an amazing thing called quantum tunneling, which actually is, although amazing, pretty normal today. Believe it or not, in all your cell phones, quantum tunneling is happening all the time. The reason our cell phones work, the reason this computer is working, is in part because of the microelectronics that work based on the rules of quantum mechanics and specifically quantum tunneling. More in the next lecture. To be continued. That's right, to be continued. I hope you have been filling out your study guides. I know it's getting really exciting. I really want to tell you all about this, but we have to wait till the next lecture. Okay, so the next video lecture, we will talk about this nuclear fusion, which is made possible by quantum tunneling in the sun, and this amazing hypothesis, which had yet to be confirmed. And so how are we going to do that confirmation or falsification? Oh, what a story this is. We'll get right to it in the next lecture. Okay, thanks. Make sure to fill out your study guides. If you have any questions, please be sure to ask your recitation instructor, ask me, ask your lab instructor. We're getting to it. This is getting really good. Before you know it, we're going to be able to understand exactly why the sun shines. Thanks so much. See you in the next lecture. See ya.